So taking a look at the big question from Friday here, the one where we have the pulley, the inclined plane, the guy inside the elevator, the ball being thrown out, projectile motion problem, all those problems all combined as one big, tough, challenging question. Okay, the first thing that I do when I see this is to draw some forces. The first force I'm going to draw is this force that acts on the elevator and the guy inside the elevator. I'm going to call that FA, although you could have called it FG or F, whatever you want. That's going to be 130 times 9.81, 130 because the guy and the elevator are both being pulled down. Okay, we multiply those together, we get 1,275.3 newtons. Now, I'm also going to want to find the force of the hill, the force that pulls this 500 kilogram object down the hill. I'm also going to need the normal force, which we'll deal with in just a few moments. We haven't done any problems where we've had to find the normal force in these questions yet. Okay, but this is one where we do have to. Mathematically, it's pretty straightforward. Conceptually, it's if you can find the force of the hill and you understand that, then the normal force isn't that bad either. Let's start drawing the forces that are acting on this 500 kilogram object. There is a force of gravity acting down, m times g. Okay, and that's going to be 500 times 9.81, not 630 or 130 or 80 or 50. There's also a normal force acting perpendicular here. We're going to call Fn. And there is the force of the hill that acts right here, perpendicular to the normal force and parallel to the hill itself. So we're calling that Fh. Now, we also have this angle in here is 30 degrees because the angle of that hill itself, 30 degrees, is always going to be the same as the angle between the force of gravity and the normal force, always. All right, so let's calculate what we need here. Let's say sine 30 degrees is equal to opposite over hypotenuse. That's going to be FH. The opposite side is the force of the hill, if we look at that triangle, over hypotenuse, m times g. So we're going to say FH, if we rearrange that, FH is equal to mg sine 30, or 500 times 9.81 times sine 30. The force of the hill ends up being equal to 2,452.5 newtons. Now, I can redraw that right here. 2,452.5 newtons. We don't have two different FHs. We have one. We just have it drawn in two different places, that's all. Okay, who's with me so far? Who's still in the game? Okay, lots of you. Good, excellent. Now, I have to find out whether it moves or not. If I want to find out whether it moves, I need the max force of static friction. To get the max force of static friction, I need the normal force. And the normal force this time is not equal to m times g. Okay, the normal force is this force right there. Let's calculate that. What side of the triangle is the normal force there? If FH is the opposite side, then Fn would be the adjacent side, right? So let's get that by using the cosine function. Let's say cosine 30 degrees is equal to Fn over hypotenuse, the adjacent side over the hypotenuse. Let's rearrange that and say Fn is equal to mg cosine theta. That's 500 times 9.81 times cosine 30. For that Fn, we get a value of 4,247.8546 newtons. Now that we have Fn, we can get the max force of static friction. FSF max. That's equal to mu static times normal force. Which is 0.20 times the normal force of 4,247.8546. We get an answer here for FSF max of 849.571. Did anybody get that? No? Yes? Now, it is possible to get this question correct without getting that max force of static friction. Okay, if you assumed that it moved, you would have still got the right answer. But we're going through this process of showing that it moves, okay, proving that it moves. All right, so how does this prove that it moves? Let's draw a little free body diagram now. We have a 500, if we straighten it out, we have a 500 kilogram mass right here. We have a 130 kilogram mass right here. Right, remember, we like to straighten it out because it helps us to determine directions there. We have FA pulling this way, not pulling downward now, it's pulling to the right with a force of 1,275.3 newtons. We have the force of the hill pulling this way, which we said was 2,452.5 newtons. And we have friction. Which way is friction going to act? Which way is friction going to act here? Take a look at the numbers here. Friction is going to act. Which way is it going to move? If it's going to move, it moves which way, Dustin? It moves to the left or down the hill. So friction is going to be acting to the right or up the hill, right? The force of friction, the max force of static friction is 849.571. I said FF, it should be FF max. The maximum force of static friction. That's the most it can be. Now, how do we show that it does move here? Since FH that acts to the right, sorry, to the left, is greater than the applied force FA and the max force of static friction, it must move. It's got to move. Listen, if it wasn't going to move, then the max force of static friction would have to take me over the top on the right-hand side, giving me a number that was bigger than the force that's pulling it down the hill. Does that make sense? Okay. It does move because we're exceeding the applied force and static friction combined that would have to be bigger if it was not going to move, would have to be bigger than the force of the hill. So it does move. So all we've done at this point is found out that it moves, which some of you didn't even try to do. Some of you just went straight to assuming that it moved. All right. Since it moves, let's get the value of kinetic friction. Let's say FKF, force of kinetic friction. We've got mu times the normal force, but this time the mu is the coefficient of kinetic friction, which is 0.10. The normal force is still 4,247.8546. There's my force of kinetic friction. So now we're going to say, instead of having this diagram, okay, instead of having the 500, the 130 with a force of friction to the right of 849, now we're going to have another diagram that looks a lot the same. 500 kilogram, 130. We have an applied force this way of 1275.3 newtons. We have a force of the hill this way of 2452.5 newtons. And we have a force of friction acting to the right, a force of kinetic friction acting to the right, because we know it moves, equal to 424.78546 newtons. So far, so good. Now, a lot of you are out of the game right now. I'm not going to ask who's still in the game, okay, because I don't want to give any indication as to who has the correct answer. Okay, there could be a few of you still in the game here, but most of you are probably going to be out at this point. All right, let's get the acceleration of this system. Okay, we can do this. The net force is equal to the sum of the forces. That's FH plus FA plus FKF. The net force is M times A. The mass here is going to be 630 kilograms, right? The total mass times A is equal to negative 2452.5 newtons, plus FA, which is positive 1275.3 newtons, plus FKF, which is positive 424.78546 newtons. Okay, even if you're out, please try to follow along. Okay, this is a good mental exercise. This is a good exercise to go through, even if you don't have the right answer. We're never going to see something this hard on a test. But when we understand what's going on in this question, the questions you do see on the test become easy then. Solve for A. Works out to be negative 1.194309 meters per second squared. Now, there could be several of you that have the right acceleration here. Okay, if you do, great. Okay, that's a challenge to get that far. Okay, good for you. There's a lot more challenge to go, though. Okay, so just because you have that right acceleration, okay, you should be pleased with yourself, but it doesn't mean we're nowhere close to having the right answer yet. Okay, that's the acceleration of the system. That's page 1 of my answer key. Page 2. Now we want to know how far up the elevator goes before the ball ends up being thrown. Right? We said that the ball is thrown 4 seconds after this system is released. If the ball is thrown 4 seconds after this system is released, then the elevator will be up in the air a certain distance before the ball is ever released. So, how far up is it? We'll say how far up before a ball is released. What I did here is said delta D is equal to VIT plus 1/2 AT squared. I said VI was 0. This is as the elevator goes up into the air. VI is 0, because the elevator was sitting on the ground, right? Then it was released, it started moving. The initial velocity of the elevator was 0. It's equal to 1/2 of A, which we just found to be 1.194309 meters per second squared, times T, which is 4.0 squared. We got 9.5547 meters. So when this ball is released, the elevator is 9.5547 meters in the air. That makes a big difference. If the ball is thrown from the ground, it's going to go a certain distance. If it's thrown from the top of a 9-meter high building, it's going to go further, right? All right. So we're going to say, therefore, the ball was thrown from an initial height of 9.5547 meters. Now, I know I saw some fist pumps and I saw some excitement from people that they got this answer. But I know as I'm looking around, people that are doing that, there's a number of people that have gotten this far, but that disagree on the final answer. So we still got a little ways to go here, okay? But again, good for you if you got that. Now what we want to find is, how fast is the elevator moving at that point? This is where we're really going to separate people. Because in the end, if the ball is thrown at an initial velocity of 20 meters per second at 30 degrees relative to the elevator, if the elevator is moving, then it's not thrown at that speed relative to the ground. We need to know how fast the elevator is moving. Okay, at the end of this distance, 9.55447 meters, the elevator is moving how fast? Vf squared is equal to Vi squared plus 2AD. Vf is equal to the square root of Vi squared plus 2AD. Vi is 0, again. So it's equal to the square root of 2 times 1.194309, not neg 9.81, times 9.55447. There were a couple ways, by the way, to find Vf here. This is not the only way. 4.77723. So the ball is moving, the elevator is moving at 4.77723 meters per second before it's ever thrown. Now, I think that was a little bit challenging. Here's where it gets even worse. Now what we have to do is find the initial x and y components of the ball as it's thrown. The initial x and y components of the ball as it's thrown. It's thrown from a height of, 9.55 447 meters. So it's like it's thrown from the top of a 9.5 meter high building. It's thrown with an initial x velocity and an initial y velocity. Let's go over to the side here. It's thrown with 20 meters per second at an angle of 30 degrees, right? Let's get the value for x. Let's say cosine 30 degrees is equal to x over 20. X ends up being equal to 17.3205. And the y component, sine 30 degrees, is equal to y over 20. Y ends up being equal to 10 meters per second. Right? So far, so good? Okay. The initial x velocity will be 17.3205 meters per second. That's how fast the ball is thrown horizontally. The initial y velocity, some of you, I guarantee you, missed this step, even if you got this far. The initial y velocity is 10 meters per second plus 4.77723 meters per second. Why did I add those two numbers together? The 10 meters per second that I just found, right, the y component of that 20 plus 4.77. Where did that come from? Yeah. Yeah, that's how fast the elevator is moving when the ball is thrown. So if the elevator is moving at 4.77, so is the ball. But add to that the y component of the ball as it's actually being thrown as a result of the guy's arm, and we get a total initial velocity as it leaves the elevator, y component of 14.77723. Now as I look out, I see the look on some people's faces like, darn it. Never thought of that. Now this question is almost easy. Not quite. Not quite. Almost easy. Now it's a projectile motion question where we have an initial x velocity of 17.3205 and a y velocity of 14.77723. The problem with this one is it's launched at a hill. So it's going to go like this, right? It's launched at the top of a building. It's going to go like this. We want to find out how far it goes. So let's say x components and y components from our last unit, right? For the x component, v is equal to delta d over delta t. And for the y component, d is equal to vit plus 1/2 at squared. The x velocity is 17.3205. The displacement there's a few of you right now, or at least one of you right now, that are like, I think I got it. I think I got it. Because so far you got everything the same. Wouldn't it be disappointing if you made a mistake at the end of all this and messed up on it? The t, what is the t? We don't know. We don't know what the t is. So let's go to the y component. The y component, we get negative 9.55 meters. That's how far it goes downwards. K is equal to the initial y velocity, 14.77723. times time plus 1/2 of neg 9.81, because that's the vertical acceleration of the ball, times t squared. Now, I'm not going to go through this process of mathematically solving for t. There's a couple of ways that you can do it. Okay, one way is to use the quadratic equation that some of you have seen, some of you have not. T is equal to negative b plus or minus square root of b squared minus 4ac over 2a. Who remembers that? Okay, or you could graph this on your calculator and take the intercepts. Okay, those would both give you the values of t. One of the values of t, when you solve for it, is negative 0.54718 seconds. The other value of t, it's kind of odd that there's two values, but there is, 3.55987 seconds. Which one do you think we want to use? Which value of t do you think we want to use here? The positive one, right? The negative one does have significance, but it's not the one we want to use. It takes 3.55 seconds for the ball to go from here to where it hits the ground. What's the significance of the negative 0.54 seconds? Yeah. Basically, yeah, if forget about the elevator for a second, if this was just a straight projectile motion question and we went back in time to ground level, we'd have to go 0.547 seconds back in time to get to the ground level. Make some sense? Okay, in the end, that 0.547 seconds has no practical meaning. It has a theoretical meaning, but no practical meaning to it. Okay, so this is the time we want. Now there's one or two people out there that are getting confident. The time here is 3.55987 seconds. Solve for delta D there, and we get 61.6 meters, or we get 62 meters. And I just saw that little grin out of the corner of my eye on Jeff's face. Ryan looked remarkably stoic throughout this whole thing. Confident, but yet stoic. The answer is 62 meters, guys. We got Ryan and Jeff, the only ones that got the right answers. Now, how many people got real close? You just made some silly little mistake. What mistake did you make, Justin? Okay. So this step right here? 3.24, okay. Okay. So, but you had an initial Y velocity of 10 meters per second instead of 14. Okay. What did you do, Javi? All right. So we have winners. This is good because I don't know how long it's been since I've had a class of two people get the answer. Like I say, it's almost always either 1 or 0. But you guys are just so smart. Yeah. All right, that's it.